Welcome to this lecture on immunology. Today, we are going to explore a fascinating topic, the factors affecting immunogenicity. Have you ever wondered why our bodies aggressively attack certain microscopic invaders while completely ignoring others? By the end of this video, you will understand exactly how our immune system makes these critical decisions and how scientists use this knowledge to design life-saving vaccines. Let us dive in. To begin, let us imagine a highly trained security guard at a building entrance. If a regular employee in uniform walks by, the guard ignores them. But if someone in a bright neon clown suit carrying a ladder approaches, the alarm sounds immediately. In immunology, this concept of standing out to the body's security system is called immunogenicity. It is the inherent ability of a specific substance, known as an immunogen, to provoke a strong, measurable adaptive immune response, like producing antibodies or activating T cells. We need to understand what makes a microscopic molecule look like a dangerous intruder. Now that we understand what immunogenicity is, let us look at the intrinsic properties that make a molecule highly immunogenic. The first critical factor is foreignness. The molecule must be recognized as non-self, because our immune system is strictly trained to tolerate our own self molecules. The second major factor is molecular size. Size is absolutely crucial. Molecules with a molecular weight greater than 100,000 Daltons make excellent immunogens. On the other hand, tiny molecules weighing under 5,000 Daltons generally fail to trigger any alarm. The immune system simply overlooks them as harmless passerbys. Building on size and foreignness, the next essential intrinsic factor is chemical complexity. A complex protein with a highly diverse sequence of amino acids is far more immunogenic than a simple repeating polymer chain, like a pure carbohydrate. The immune system looks for intricate, unique patterns to identify threats. Finally, the substance must possess susceptibility to biological degradation. This means the host's enzymes must be able to chop the molecule into smaller pieces. These smaller fragments are then presented to immune cells on specialized receptor molecules, which is a mandatory step for activating the full immune response. Beyond the physical traits of the molecule itself, we must also consider external and host-related factors. The genetic makeup, or genotype of the host, dictates which specific immune receptors are available. Two different people might react completely differently to the exact same molecule based on their inherited genes. Additionally, the dosage and the route of administration, whether injected into a vein, under the skin, or swallowed, drastically alter how the immune system encounters the threat. Scientists also use special substances called adjuvants. These are mixed with the immunogen to artificially boost the immune response by creating a localized inflammatory reaction. Understanding all these interacting factors is absolutely critical in modern medicine. When scientists design a new vaccine, they must carefully select and modify viral or bacterial components to ensure they are highly immunogenic, guaranteeing that the patient develops strong, long-lasting immunity. Conversely, doctors face the exact opposite challenge in organ transplantation or protein-based drug therapies. Here, they must actively minimize immunogenicity. If a transplanted kidney or a biological drug is too immunogenic, the patient's own immune system will attack and destroy the life-saving treatment. By masterfully manipulating these variables, medical professionals can precisely tune the human immune system. While immunogenicity is a biological concept, We can mathematically evaluate the strength of the immune response by looking at the binding affinity of the antibodies produced. This brings us to the equilibrium association constant formula, derived from the law of mass action. Ka represents the equilibrium association constant, measuring the strength of the binding in liters per mole. In the numerator, we have the molar concentration of the bound antigen-antibody complex. In the denominator, we multiply the concentrations of the free, unbound antigen and the free, unbound antibody. When immunogenicity increases, the immune system produces better-fitting antibodies, driving the bound complex up and the free molecules down, which makes Ka much higher. Now that we have our formula, let us see this with a concrete example. Imagine we are testing a large, highly complex bacterial protein called antigen X to see if it would make a good vaccine. Because of its large size and complexity, we expect it to be highly immunogenic. After injecting it into a laboratory model, we measure the equilibrium concentrations. The bound complex concentration is 1.0 times 10 to the negative 4 molar. Both the free antigen and free antibody concentrations are measured at 1.0 times 10 to the negative 6 molar. We need to calculate the association constant to quantify the strength of this immune response. Let us set up the calculation to find exactly how strongly the immune system reacted to antigen X. We start with our equilibrium association constant formula. We substitute our measured molar concentrations directly into the equation. The concentration of the bound complex goes into the numerator. Then we place the product of the free antigen and free antibody concentrations into the denominator. This sets up our ratio for calculation. It is very important to keep the units consistent during this substitution. In the next step, we will simplify the denominator to see how many molecules remained unbound. Continuing our calculation, we first multiply the two free concentrations in the denominator. When multiplying numbers with exponents, we add the exponents, giving us 10 to the power of negative 12. This extremely small number represents the tiny fraction of molecules that remained unbound, showing almost all molecules successfully found each other. By dividing the numerator by the denominator, we find that the association constant is 1.0 times 10 to the power of 8 liters per mole. This very high value physically means the antibodies bind extremely tightly, confirming that the large size and complexity of antigen X made it highly immunogenic. To truly appreciate the impact of molecular complexity, let us test a different substance, antigen Y. This is a simple, repeating carbohydrate polymer with a very low molecular weight. Because it lacks chemical complexity and size, we suspect it has poor immunogenicity. We inject it into the same laboratory model. This time, the bound complex is only 2.0 times 10 to the negative 6 molar. The free antigen and free antibody are both much higher, at 1.0 times 10 to the negative 4 molar. We must calculate the association constant to compare it against our complex protein. We will apply the exact same equilibrium association constant formula to mathematically prove how the lack of chemical complexity negatively affects immunogenicity. We substitute the new, lower concentration of the bound complex into the numerator. We then place the higher concentrations of the free, unbound molecules into the denominator. This setup directly mirrors the physical reality inside the test tube, where most of the molecules failed to bind. We expect the resulting value to be significantly lower than our first example, highlighting the biological importance of molecular complexity. Let us finish the calculation for our simple polymer. We calculate the denominator by multiplying the free concentrations together, giving us 10 to the power of -8. This represents a large pool of unreacted molecules. A larger denominator mathematically guarantees a smaller final fraction. Dividing the terms, the final association constant for antigen Y is only 200 liters per mole. This value is drastically lower than the 100 million we saw for antigen X. This mathematically proves that because antigen Y lacked large size and complexity, it was poorly immunogenic and failed to generate a strong antibody response. Now that we have proven the math, let us visualize these concepts together in this diagram. In the center, you see an ideal immunogen, represented by a complex, folded protein structure. Notice the 4 arrows pointing toward it. These represent the 4 intrinsic pillars we discussed: foreignness at the top, large molecular size on the right, chemical complexity at the bottom, and degradability on the left. Below the protein, look at the horizontal scale. It perfectly summarizes our lesson. On the left, in red, small, simple, and self-like molecules result in low immunogenicity. As we move to the right, in green, large, complex, and foreign molecules result in high immunogenicity. We have covered a lot of ground today, so let us summarize the key takeaways. First, immunogenicity is not a simple yes or no property, but a complex scale determined by multiple interacting factors. The primary triggers for the immune system are the molecule's intrinsic traits: its foreignness, large size, chemical complexity, and degradability. We also learned that these traits are further modulated by the host's genetics, the dosage, and the presence of adjuvants. Finally, we saw how calculating the equilibrium association constant allows us to mathematically prove the strength of the immune response. By mastering these factors, scientists can engineer highly effective vaccines to protect global health. Great job following along.